What's differentiable? Okay, so what is differentiability? We know what is defined. Defined is when we have x value, we have a y value for that point. What is limit? Limit is when we go from the left approaching the point and go right hand side approaching the point, they're approaching to the same value. That means the limit exists. What is continuity? Continuous is at that point is connected. There's no jump, no open circle, no any like asymptote, something like that. It's connected. That's continuity. And we have three rules, well, 3 steps needs to satisfy. Then we say this is continuous. First of all, we need define, and then we need limit exists, and I need the defined value is the same as the limit value. That is the continuity. So what's the last one? Differentiability. What's differentiable? Okay, what is differentiable? Function f is said to be differentiable at x equals to a if that exists. Okay, if that exists. But that's not really the formula we use. Okay, that's not really the formula we use. When the limit, let's just do that. Let's just write what is not differentiable. Let's say that. In order to say what is differentiable, let's think about what is not differentiable. Okay, anything not continuous. Well, not continuous. You remember I said if it's not defined, then it's not going to be continuous. It's not going to be differentiable. If it's not defined, if its limit doesn't exist, it's not going to be continuous and it's not going to be differentiable. So I can have not continuous overall. So why is not continuous? It might become because there's a jump and then the limit does not exist. It might become there's an open circle and then it's not defined and then it's not continuous. But anyway, it's not continuous. If anything you recognize, say this is not continuous at that point, then it's not differentiable. Okay, if it's not differentiable. But how about if anything is continuous? Okay, like somehow is continuous. The second thing is when it's continuous. Okay, do you think this point is continuous? Yes or no? Yes. But do you think this point is differentiable? Okay. What's differentiability? Is the gradient, right? Is the derivative. Like, do we have derivative at that point? Let's say this point is -2. Okay, when x equals to -2, what's f dash x equals to? Okay, what's f dash x equals to? Why I would say there's no derivative at that point? If you think about this is fx equals to -2x minus 4. And for that side is gx equals to x plus, is just x. Okay, just gx equals to x. What's the derivative of fx? What's the gradient of fx? -2, right? F dash x equals to -2 until like the point -2. What's g dash x equals to? 1. Okay, so all the other points is fine, but for that point, which one do you take? Do you take -2 or do you take 1? Well, you can't take both, like it's not the same value. Therefore, it's not differentiable because the left-hand side limit and right-hand side limit is not giving you the same thing. Then it's not differentiable because I don't know which one I should take. Like, that's the problem.
That means that whole function is not differentiable.
No, only that point. Only that point. Other point is fine because it's only follow one function. But only that point is at the intersection of two functions. And then I don't know which gradient I should take. Like it can be that one, can be that one. If you see from the left, if you see from the right, it will be the same thing. But I can't tell. So second case is not differentiable when it's a sharp point, a sharp change in direction. Well, you can say a sudden change in direction. That's the second case. I cannot derive that. I can't find the differential. It's not differentiable at that point when there's a sudden change in direction. This is very sudden, okay? A linear and very sudden change. Well, it can have sudden change for other functions, but not that obvious. For example, that is a sudden change as well at that point. Okay, that's a quadratic. And that's a linear. Okay, that can be a sudden change as well. Why? Because the gradient on the left-hand side of the function is different from the gradient of the right-hand side of the function. If you think about the gradient at that point on the quadratic, it's a horizontal line. Okay, that's the tangent of the point. But if you think about the linear gradient, it's not necessary to be the same as the pink one. So that's a sudden change in the direction. So we don't have derivative at that point either. Okay, that's the reason. If it's continuous but still not differentiable, that's the reason why. And the third one is so important. That's the one students always forget, is the endpoints. Endpoints is not going to be differentiable. Doesn't matter it's open circle or closed circle. Even as a closed circle, like closed endpoint, can't be differentiable. So cannot. Both of that you cannot differentiate. So you don't have derivative at both points. Okay, at both points. Endpoints cannot be differentiated. So not continuous point is not going to be differentiated. Any point is continuous but with a sudden change in direction at that point, like you change functions at that point, is not differentiable. Well, fx and gx are two functions and they are connected, not necessarily always not differentiable. Okay, in some cases it will be fine. It's just the derivative on the left hand side of the function is the same as the derivative on the right hand side of the function, then it's not differentiable. Otherwise, if you have one same point but the derivative is different on both functions and they connected, I don't know which one I should take, then we'll say it's not differentiable. Okay, then we'll say it's not differentiable. And endpoints is not differentiable. Okay, endpoint is definitely not differentiable. So that's what we need to know. All right, so that's the three things is not differentiable, and you need to remember that. Okay, on your derivative function, you will draw open circles for all of that point because there is no derivative at those points. Okay, there's no derivative at those points. What points? Not continuous point. Continuous point, but the direction sudden change. And for endpoints, the derivative of those points will be open circle. You don't have derivative on those points. Okay, let's have a look. What is differentiable? Okay, so what is differentiable? Well, any function is differentiable. Like any function with no restrictions, no asymptotes will be differentiable anywhere. But what we need to worry about is when we connect two functions. Remember when we talk about continuity is the function itself is no problem. It's just when we're trying to connect the point, then we might have some problem. It's the connection point might get problem. So what we need to talk about now is function can be joined if they intersect. But they can join smoothly or not smoothly. Something can join, but not necessarily joins like smooth or not smooth. Okay, so not necessarily join smoothly. What is a join smoothly curve? Let's see. This point I can say is join smoothly. Okay, it's almost kind of very smooth. That's not join smoothly. You can see there's a sudden change in direction. So what we worry about is the gradient at the same point on the two different functions. If the gradient on this one is the same as the gradient on this one, then it's called smoothly connected, smoothly joined. If something like that, the derivative on both sides are different, then it's not smoothly joined. They both join, they're both continuous, but they're not necessarily differentiable at that point. So if we say fx is two functions, f1x and f2x, okay, that's the two function. The domain for f1x is negative infinity to a, and for the second function, a to infinity. Okay, so that's the two hybrid function. If f1a equals to f2a, that means they intersect. Okay, they intersect. If f1a equals to f2a, one open circle, one closed circle, they're at the same point, which means they joined. Okay, first of all, they're connected, they are continuous. If they are not the same, there's no point to talk about differentiability after that. And if the derivative of the top function put a in will be the same as the derivative of the second function you put a in, that means smooth. Okay, they join smoothly. Okay, they join smoothly. Whether smooth or not, it depends on the derivative. Whether they join or not depends on the y value. If they have the same x, same y value, which means they joined. But if they have the same gradient at the same point on two different functions, which means they join smoothly. Okay, they connect smoothly. Okay, so for if two curves are joined smoothly, then first one they need the curve intersects, that's the first one here, and they need the point of contact have the same gradient. Okay, have same gradient for both functions at that point. Okay, at the contact point. For this example, we don't want it. It's no longer important. We don't want the example one. That's the first principle thing. Forgot to delete it when I added. So we don't need that. Wait. Just go back. I'm not using this. I'm not using first principle to prove that it's not differentiable at x equals to 0. But let's find the derivative. Okay, just find the derivative for this function. Not first principle. Just find the derivative of that function. What's f dash x equals to? Do you have that? Y is not differentiable at 0. If you put 0 in, what happened? Yeah, it's undefined. Denominator is 0. So f dash 0 is undefined. Okay, when you put 0 in, the denominator will be 0. Okay, so f dash 0 is undefined. But, like, it's not important really talk about this single question here. Like, I can see that it's really easy. But if I say so y equals to x to the power of n, dy dx equals to n times x to the power of n minus 1. In which case, f dash 0 will be undefined. N is what? Then f dash 0 is undefined. Okay, for if like x squared, if it's x squared, the derivative is 2x, right? Derivative is 2x. F dash 0 is defined, right? It's working. In which n, for which value or which values of n, your f dash 0 will be undefined. Less than 1. If n is less than 1, equals to 1 is fine. Okay, less than 1, i.e. n less than 1, then f dash 0 is undefined. Okay, you must remember that. That's really important. Year 12, I have a multiple choice questions, and a lot of students just forget about it. They can actually get it right, but they all forget about that. For hybrid function, like I think the question is a hybrid function with a power function on top and another function at the bottom, and they ask which point is not differentiable. All the students is only focusing on the connection point, like they only test whether the derivative of the left equals to the right at the connection point, and they completely forget for the power function itself there's a restriction. For the power function, when the power is less than 1, you can't derive the function at x equals to 0. Because why? Because if n is less than 1, n minus 1 will be less than 0. Okay, will be less than 0. So what I can do is n over x to the power of 1 minus n. Okay, we will have that. N over 1, flip it, that can becomes negative 1 minus n. So 1 over x to the power of 1 minus n. Because n is less than 1, 1 minus n is a positive number. And then if you put 0 in now, that's denominator equals to 0. So it's undefined at f dash 0 is undefined. Okay, f dash x 0 is undefined. So when you have power function, when your power is less than 1, remember the derivative is not defined at x equals to 0. Okay, at x equals to 0. Also, well, you don't know the graph. Can't do that with you now. But that's just from a formula. Okay, that's just from a formula.
What if we got bracket?
Same thing. If it's less than 1, it's still denominator. Like you still flip it down. Like the same thing. Okay, so that's the important thing I want to talk about for this question. I'm not really want to use first principle, but what I want to do is talk about power function. When power less than 1, the derivative is not defined at x equals to 0. Okay, let's go to the next page. For next page, we have R mapping to R fx equals to x if x greater equals to 0, equals to minus x if x is less than 0. First of all, can you sketch this hybrid function for me? Like just sketch this hybrid function for me. Do you have that? Which point is not differentiable? 0. Okay, why 0 is not differentiable? Yeah, like more detail is sharp. What's the derivative on the left hand side? Negative 1. Oh, negative 1. What's the derivative on the right hand side? 1. So negative 1 is not the same at the same point, which means the derivative is not differentiable. I can't find the derivative at x equals to 0. So what, again, this is the fx function, right? This is the fx function. That's the x. If I want to draw f dash x function, what you can do? F dash x, I want to draw the f dash x and x function. This is f dash x. And this is x. What do you do? What's the derivative when y equals x? 1, right? So when x greater than 0, I just have 1. Okay, when x less than 0, what's the derivative? -1. Okay, y equals to -x, the derivative equals to -1. What else I need to do? Yeah, so what happens to the endpoints? Open circles. Okay, so I don't have derivative at x equals to 0. Because if I have closed circle there, which means when x equals to 0, derivative can be -1, can be 1. So I don't put any points there. Okay, I don't put any points there. So it's an open circle. So it is differentiable anywhere else except x equals to 0. Okay, except x equals to 0. First of all, it is continuous. You can see sub x equals to 0 into both functions, we get 0. So it is continuous. Then we find the derivative for both functions is 1 and -1. So at 0 is not the same. So we will not have derivative at x equals to 0. So if we write the derivative function, it's still a hybrid. That's what I'll have. Okay, that's the hybrid function, but we don't have 0. Can you see we not included 0 in? Alright, draw the next one, please. Okay, sketch the fx function first, and then think about the f dash x. Okay, if you finish sketching the graph, just have a look at my sketch. Well, for this point, you can't see an obvious change in direction here. Like, I don't know, it might be a sudden change, it might not be a sudden change. So I need the equation to, well, ignore my pink graph, just look at the blue one. The blue one is what the graph looks like. Okay, so quadratic, because the first one is x plus 1 squared, I should have minus 1 as my turning point, the full graph like that. I have y-intercept at 0, 1, so I have the part greater or equals to 0, so it's only this part of the graph. Okay, this part of the graph. So I have 0, 1, 4 like this. And then the other part is linear. I have x less than 0. So when we sub 0 in, it still give you 0, 1. So it's a connected point. And I have negative a half 0 as my x-intercept. So this is the blue one is my graph. And also I can't see whether it is smoothly joined or not. Okay, so hard to tell. So what I'll do here is I give the name differently for two functions. I said f1x is x squared plus 2x plus 1. f2x is 2x plus 1. Okay, and separately name two functions. Then I can do the derivative of the top function is 2x plus 2. The derivative of the bottom function is 2. And I can sub 0 into all these four functions. When I sub 0 into the top two, I get both 1, which means the function intersects, which is this point here. Okay, 0, 1. I have intersection at x equals to 0. And I sub 0 into the derivative function. In both derivative function, I have 2 and 2, which means the gradient is the same for that point on different graphs, on different functions. So it is smoothly joined. So x equals to 0 has derivative. X equals to 0 is differentiable. Okay, x equals to 0 is differentiable. The derivative value is 2. Because on the left function I have 2, on the right hand side function I have 2 as well. So therefore my f dash x function will look like this. Okay, I can write the rule looks like this. F dash x equals to 2x plus 2 and 2 when x greater equals to 0 and when x less than 0. I can have equal to 0 here because it is differentiable at x equals to 0. So I will include 0 there. But I only include 0 once, okay, I'm not going to include another time at the second function. So which one I included, it doesn't really matter, but I just follow what we have before. Yeah, that's the definition. The gradient on the same point should be the same for both functions. Yeah? So what's the derivative of this graph? The left hand side is -1. The right hand side is 1. They are not the same. So they are not smooth and it's not differentiable. The same here. What's the derivative on the left hand side? It's 2. What's the derivative on the right hand side? It's 2 as well. They are the same. Then it is differentiable. It must be a closed circle because I said it is differentiable. If it is differentiable, then you have a point there. When x equals to 0, your derivative is 2. So which means f dash 2 is 0. F dash 0 is 2 in this question. Okay, your f dash 0 is 2. Your derivative at x equals to 0 is 2. It is differentiable. Okay, it is differentiable. Why is it open circle before? Because it's not differentiable at that point. I have different values for derivative. That's why it's not differentiable. So my derivative graph looks like this. Okay, the pink one is my derivative graph. The blue one is my fx and the pink one is my f dash x. So I have 0, 2 is the connection point. They are connected, which means on different function, I have gradient same for the same point. So I have derivative at x equals to 0. Have a linear on the right hand side and the horizontal line linear on the left hand side. Any questions? All right, next one. about the differentiability for the function with that rule. Okay, with this rule. Okay, again, I want to sketch. Well, I'm not going to sketch fx function this time. I will only sketch f dash x function for this graph. So the connection point is 0. Okay, they connect at 0. Domain is -5 to 4. -5 to 4. So what I want to do is I will name the function. f1x is the top function. fx squared plus 2x plus 1. f2x is the linear, which is x plus 1. f1 dash x equals to 2x plus 2, and f2 dash x equals to 1. Okay, list the function, derive that. So f1, 0, because 0 is the connection point, that's the point I want to investigate. So that's 1. f2, 0 equals to 1. This tells us is intersect and is continuous. But f1 dash 0 equals to 2. f2 dash 0 equals to 1 still, which means not smooth. X equals to 0 is not differentiable. What are the points that's not differentiable on this graph? What is it? -5 and 4 is not differentiable because they are the endpoints, and you know endpoints is not differentiable from previous page. Okay, endpoints is not differentiable. So when we write about the f dash x function, what we'll write is 2x plus 1, 1. The derivative is 0 to 4. And this is -5 to 0. It's not inclusive for all the endpoints. Okay, it's exclusive for all the endpoints. So 0 is not exclusive, it's exclusive, 4 is not in, -5 is not in, and 0 is not in. This is not differentiable. I can't derive. They are different. They don't have the same gradient. Which function are you talking about? The original one is a closed circle, but the derivative is an open circle. I'm talking about the derivative function. It can't be differentiated. So what if I sketch for this one? This is the f dash x function. This is the x. So 0 and 2, which must be an open circle here. And for the point 4, I have 10. Which must be an open circle as well. So that's 4, 10. And then here's 0, 2. Open circle here. And then I have 1. That's 0, 1. Until -5. So open circle here, -5, 1 as well. So the derivative function will look like this. Okay, 4 open circles. Okay, 4 open circle. Negative 5, 1, 0, 1, 0, 2, and 4, 10. Okay, 4 is not differentiable because it's the endpoint. Negative 5 is not differentiable because it's the endpoint. 0 is not differentiable because it's not a smooth point. Okay, it's not a smooth point, so it's not differentiable. All right. That's this question. Well, this shows you all the situations when it is differentiable and when it's not differentiable, what you should do to your f dash x function, what you should do for your f dash x graph. Okay. 2, 3, 4. I have shown you 2, 3, and 4. For next 18 minutes, I want you to try example 5. Okay, example 5 is 3 hybrid function, but it's the same idea. If I said they join smoothly, which means they join and the gradient at that point, the connection point will be the same. Okay, so tomorrow we'll go through this question. Okay, tomorrow we'll go through this question. I want you to try that first by yourself, find ABCD values, and set up simultaneous equation and find ABCD values.